We come to the last panel of today's round table discussion. It's a big pleasure to continue. Eivind already summed up very nicely the challenges and said there will be a lot of work for the Hagerbach, hopefully. My name is Michael Kompatscher. I'm the General Manager of the Hagerbach Desk Gallery here, and it's a big pleasure to be also the home of the Subspace Energy Hub, to be here where we do this discussion. And I'm very happy today that this is the first roundtable we do talking about hydrogen, the hydrogen topics. And yeah, some of you were already on the table, but we have two new panelists also here in our round. This is Professor Maurizio Barbato from the Southern University of Ticino. You will introduce yourself shortly with your presentation. Then we have Franz Noser here from Elkuch. Elkuch is one of our shareholders, also from the Hagerbach Desk Gallery, and they have very special solutions also for hydrogen. So I think it's great to have this contribution also from an experience side involved, because the panel topic now is really to talk about opportunities. We know about demand, we see there is need, we see there are challenges, but to give a new perspective also and to see what are the opportunities then also for a test environment, as we have here as a research infrastructure that we are since more than 50 years. Currently candidate also of recognition as of national importance here in Switzerland. I think really we want to contribute with what we have here to the topic, to the change, also to the society. For this we have this partnership of the Subspace together, and we really want to do this, to accelerate this, and not just to wait until 2050 to find out we are too late. So setting the scene with this, Maurizio, I give the word directly to you. Maurizio will give us a different perspective from his experience on a similar topic, but helping us with the discussion.
Yeah,
thank you
very much. Hello, everyone. In fact, my topic is not strictly related to hydrogen, but as you will see, there are connections probably, and probably also possibility of synergy. Okay, so my name is Maurizio Barbato. I'm professor at the University of Applied Science of Southern Switzerland, that is located in Ticino, in Lugano, by the way. So you see, the University of Applied Science are around Switzerland. We are 9. And the southern one is the my university. Okay, this is a perspective of all the university structure in Switzerland. There are University of Applied Science and University and Polytechnics. You know that there are 2 polytechnics and a certain number of universities. And in Ticino we have both a university and a University of Applied Science. What is a University of Applied Science? We produce engineers that are directly applicable to, let's say, to the industry. Just to say a few words about where I am. This is the structure of formation of my university. So it's located in Ticino with 2 branches, northern of the, a bit northern of my canton. And I am from the Department of Innovative Technologies. So I deal with mechanical engineers mainly, then with also electronic informatics and data science engineers. But main field is with teaching and making research with mechanical engineers. Okay, this is my institute. My institute is formed by almost 46 people. Oh, I'm going too fast. Yeah? 50 people, unfortunately just few female, but you know that science is not too practiced by females. That's unfortunate. We promote also female students, that it's important for us. And that's important especially for new generations. Anyway, just to tell you which is the reason why I'm here, because I want to tell you about an example of how we can store energy in underground. And one study that we did since many years it's related with compressed air energy storage. I don't know if you are familiar with this technology. This technology deals with a very simple, let's say, division of the Brayton cycle. Brayton cycle is the gas turbine cycle. You can cut this Brayton cycle in two, and you do first the compression storing energy. So you use the compressor of Brayton cycle just to compress air, but this compressed air is sent to a cavern. How you can compress air? You just use electricity from the net. So you just get electricity from the net, you compress the air, you send the air underground, you keep this high pressure air sealed underground, and when you need your energy back, so you need your electricity back, you just extract this high pressure air, you make this high pressure air expand in a turbine. Obviously you need some fuel to do that, because you need not just high pressure, but you need high enthalpy, so you need also high temperature, and so you can expand this and get electricity back. The round trip of this system can be, tested in real plants from 43 to 54%. So the two existing plants that are just, one in Germany and one in US, have this kind of efficiency. There is a new one that has been claimed in China, just as I was just saying during lunch, was started, connected to the grid in the 4th of April last month, 2 months ago, sorry. And this one has an efficiency claimed of 70%. But this is the amount of efficiency you can get with just a KAES process. So the process that I just simply described to you gives an efficiency like that. Why? Because obviously you have some losses in compression and expansion, but you have also to use fuel to rebuild the temperature of the extracted air. You know that we cannot store air at very high temperature, so we store air at low temperature. This means low temperature can be 30, 40 degrees. The CO2 balance in this plant is obviously positive because we burn gas. This diagram was presented in another form. This is the Ragone diagram, in which you see the energy stored on the abscissa and the ordinate. You have the power output, and you see the classification of different energy storage systems. And you see that the only one that is comparable with pumped hydro, that is the one that we use for storing energy. You have to think that in 2021, now it's a bit changed thanks to batteries, but in 2021, 95% of the energy, electrical energy in our plant was stored via hydro pumping. So this was this way of storing energy. The rest were batteries, flywheels, ultracapacitors, and etc. Now batteries are gaining their space, but you see that when we go towards large quantity of energy to be stored and large power to be produced, there is still one winner, that is hydropower at the moment. And KAES, that is compressed air energy storage. So this is a possible way of producing energy, even though, and I tell you, the oldest of these two plants was built in the 70s. So from the 70s to today, 50 years, just two plants are operating. So this means that there is a problem around. Okay, so from the Ragone plot, we see that this technology is able to have performance comparable to hydropower, and is still competitive in terms also of costs. It's still competitive, and it becomes much more competitive if we exploit thermal energy storage. So if we combine mechanical energy storage, that means not just compressing the air and store air at high pressure, but also keep the thermal energy that when we compress, we pump into the gas. So we have, after compression, high pressure, high temperature. This temperature today is wasted. Instead, if we store also temperature in terms of internal energy, so thermal energy storage, we can increase the efficiency of these systems up to 75%, sorry. So, and why we can apply this technology in Switzerland? Because we can exploit mountain, and so this means underground spaces, and then we pass from decays to adiabatic cays. This is an evolution, possible evolution, that brings the costs similar to the costs of hydropower and hydro pumping. Okay, just let you see how this adiabatic compressed energy storage works. As before, we compress air thanks to a compressor. This high pressure, high temperature air is sent to a thermal energy storage. Thermal energy is left there, and then we store cold air in a cavern. When we want to extract the power, we just, and you see that there is just one component more, that is, by the way, that's important, that is inside the cavern. Because if you keep this component inside the cavern, the costs are accessible. If you keep this component outside, you have to deal with a component that has to stand high temperature and high pressure. And this will mean very high costs for a big component like this one. So you needed to have this component inside the cavern, as you will see in a minute. When you want to extract energy, you just reverse the process. You extract the air at high pressure, you make the air passing through the thermal energy storage, and then you get high enthalpy air. This means high temperature, high pressure air, and you expand that in a turbine, and you produce electricity back. And this gives you an efficiency that is above 75%. This has been tested experimentally. This was the story of the research done in this field by different research centers. One is my university, one is ATH, and different companies that were involved in the research in the years, and with the different financing sources that also include the Federal Office of Energy, with which Stefan was one of our promoters. This was also one of these works was also dealing with a real scale experiment. Real scale experiment means a tunnel of 120 meters in which, in Polleggio, that was a service tunnel for the Alp Transit, tunnel, that was a tunnel to bring the materials from one valley, from the extraction point to another valley to the deposit, the final deposit. And this was a site that was just built to test a technology like this one. And this was the first AKS pilot plant without turbine realized in the world, and some other records belonged to this project. But just to tell what it was, imagine this tunnel, just 120 meters were excluded and were closed by two concrete plugs. And these two concrete plugs contained the storage volume. Inside the storage volume, you can see the thermal energy storage that is inside the high pressure region. Part of the cavern was lined and part was just bare, just to test also the behavior of the different finishing of the cavern. And the idea was to compress the air at high temperature, inject the air, store the thermal energy here, and have the high pressure air stored inside the cavern. Just to tell you what the test was just a container with gravels, and the air was coming from top, releasing the thermal energy to the rocks, and then coming down cold. This was the thermal energy storage for the sensible part. But, and this is, as you could see it inside the cavern with the section that is that one. Sorry, this figure is flipped. And this was the dimension of this system to keep the the thermal energy, the hot air, leaving the thermal energy there up to 550 degrees. This was working at this temperature at the time. Was not alone, because beside this big one, there was a small one that is a special thermal energy storage just to keep the temperature constant, thanks to the fusion of a material that can fuse, that can be melted at very high temperature. This was a very small thermal energy storage containing some pipes filled with alloy, with aluminum, copper, and silicon that can melt at 520 degrees. Why this is necessary? Because when you get back the thermal energy, as a reduction in temperature during the extraction. But your turbine likes to work at constant temperature. So if you put something that is melting as the last step of energy extraction, your temperature is kept at the melting temperature of your metal. So you extract your temperature at with very high values, and this means very high value also for the energy you are extracting. This system worked, and with this system, without the turbines, the efficiency was demonstrated to be around 75%. Why without a turbine? Because once you know, the mass flow rate, the temperature and the pressure of the fluid that is coming out, you know what is the energy you can get from your turbines. Just depend on the manufacturer you use. So the turbine were not installed. So what were the lessons learned from this experience? By the way, this is not existing anymore, this site. Amberg was participating in this project, by the way. Is not existing anymore. The gallery has been given back to the canton as it was, so it's clean up. There are not anymore even the doors or even the plugs. The experiment was not a complete success due to problems with the plugs. The plugs were not sealing very well the tunnel, and also the pressure target was aimed at 33 bars, but the maximum pressure reached in this 120 meters piece of tunnel were 8 bars at the end. So a bit far from the final target. What we learned was that the technology is comparable in terms of performance to, and especially efficiency performance to pumped hydro. Some elements that are used in this kind of plants come from other technologies already mature, so you don't have to study special apparatuses for realizing that. The thermal energy storage works, and this increases the efficiency up to the point that makes things comparable with hydropower. And the combination of latent and sensible tests, as I told you, can keep the temperature at a level in which the turbines can work steadily and with high efficiency. This is the last point. It could be even with a question mark. We concluded that this technology could be applied to our country, but is not mature to do that. Why? Because we have some challenges. And one of the challenges, and this is the challenges that probably make you understand why I'm here, is that we need ceilings for these caverns. If we don't have ceilings, we cannot store very high pressure air for a long time. Long time can even mean for us days, not months. Obviously, these are not a seasonal storage, but it's a daily storage. So the good sites can be found in Switzerland, but the problem that we find now is really the sealing. The sealing technology and the sealing way to make the cavern really suitable for these high values of pressure. Values of pressure that go from 70 up, from 70 bars to 100 bars. And another point that emerged today is this, that pilots will require large investments. Even testing a lined cavern in the right size to have the right answers takes millions. And this is one of the problems. And this emerged already today in Willy Pascal that made the crude numbers quite evident. Okay, thank you very much. If there are questions, then the panel will come.
I will hand over at this stage that we go through the rest of these slides directly to Franz from Elkuch, because he has also to bring some real experience with hydrogen in this case, not compressed air, but on a different scale, not of a cavern scale, but I think you can tell us a bit of your experience. Please.
I will do it. Thank you. Good. Thomas, wie ist es gerichtet? Das ist richtig.
Okay, these are mine.
Sorry.
So you
One
go
more?
ahead, yes.
This goes back. This one.
Yeah, it's missing a...
So. Hello. I'm Franz Noser. Michael told you. I'm a sales manager at the Elkuch Group. I'm a dinosaur in this company. I'm a very long time there. It's very pleased to say you, so no, tell you something about things like that. The Elkuch Group is a company based in Huh? Okay, sorry. Elkuch Group is a company based in Liechtenstein. It's founded in 1949 by Ludwig Elkuch, and we are about 300, 400 employees. We have some locations and workshops also in Switzerland and in Germany. In Germany 1, in Switzerland about 5, and then we have also some sales offices around Switzerland. Turnover, it's about 100 million euro. So, I told you we are in Liechtenstein. The calculation, the design and manufacturing and testing of the tank, it's all in our house in Wenden. There are some pictures, you can see that. And yeah, we go to the next point. You can see this little tank. For example, if you want to fill it up with 30 bar, then my bedside lamp will give me a light for about 30 hours. This little energy, you can drive the Tesla Model S about 30 seconds. You can see then how much energy we use for traveling or for traveling, for moving. This little bit just for 30 seconds. Here you can see a filling station with a vertical tank. That's mostly, it will be built like this. Also we built some tanks like this. Tanks like here in the underground, the tank will be lifted down in a pit, will embed it with the sand, and then covered with earth. And the surface on the top, there are different ways possible. I will show you later. Come back to this little tank. I mean, we produce normally about 90,000 liters. So this one, just a little bit bigger. The diameter will be 3 meters, and it's about 10 meters long. On this picture, you see, from the electrodes comes inside 30 bars pressure, and then we have just one connect here to our heater or something like that. Then there are other possibilities to do this. If you do the same with gas bottles, with just 30 bar, then you need 1,800 bottles. There's one thing that you need a lot of space, and then you have another thing, you have 1,800 connections. It means each connection can be, or can give a leg for you. And when you see this, there's just one connection. Good. Over the tank is now undergrounded, and then you have a lot of possibilities where you can have on the surface. On the left-hand side, there is a park space. You don't see the tank you can use, for example, for a park space. Or in Brüten, There we built 2 tanks in the years 2014, and there is the back house garden and the playground behind there. You cannot see something about the tank. And in Britain, they have just the tanks in the ground, and they don't have a power line or something like this. They live just from the tanks. Good. Was a short thing. Thank you very much.
Thank you, Franz. Very nice. I think we can say that Elkuch is one of the suppliers that most of the hydrogen filling stations currently in use here in Switzerland are supplied directly by Elkuch. And I think so in the further discussion this will also be interesting for the experience that you got out, where the big points are, where the pain points actually are, that we can support with additional tests and with new technology and also going up in dimensions that we have heard in earlier panels today. But I will give the word to Anmol at this stage also, because I was happy. I said no more slides. We already had a lot of slides, but I asked him in particular to bring some slides about the Hagerbach Test Gallery, because for Fortescue we did some preliminary investigation also how this could be used. And as we are here as a subspace energy hub and want to make a better use out of this, and this is the further discussion, also I think it's good that you give some of your understandings and what you put together from our side, please.
Thank you. There you go. Thanks. Oops, I'll go back. Thanks, Michael. Yeah, so as Michael said, when we were working with Fortescue, we were looking for test facilities. We mentioned earlier about using underground mines or remote workings in Australia. Not quite feasible. One of the reasons was the lack of infrastructure around there. So we did approach VSH at that time, and Michael and his team were very good to guide us around. And so just a quick summary of what we learned of potential for testing. We all said earlier on that there's a lot of information out there, but it's quite limited in terms of publicly disseminated knowledge. So someone needs to take the first step and start testing, and perhaps this is the place for it. So what Michael gave us initially was the plan layout of the test gallery and the various geologies. So we've got the blue, we've got a limestone geology here, a schist and shale in this area here, which we can see when we walk in. So I think I mentioned earlier on that one of the aims of especially the Fortescue project was to look at how different geologies react, not just massive hard rocks, etc. And can we open up the storage from geology? So again, a little bit of a heavy slide, but I did this in a bit of a rush. However, what we were able to do then was superimpose the plan survey of the test gallery with the various geologies of limestone up here, slates and schists, etc. I think these are sandstones, I'm not quite sure anymore. But we were able to overlay it onto the contours of the mountain. And some of the things that we thought we might be able to get out of doing tests here was to demonstrate the technological readiness of the overall gas storage. So I mentioned, that there is a need for technological assurance, and there is a lack of standards at the moment, and this facility provides potentially an avenue to demonstrate that, and then also construction difficulties. So what Michael and his team had demonstrated was that there are sites accessible here that we can start construction out of. So the constructability aspect can be quickly demonstrated, and again, all the infrastructure is here to do that. So it's not a huge mobilization process. Validate actual real-world behavior. So we've got different rock masses here. Instrumentation and monitoring, etc., can be put in as we need, and start to measure response of the rock mass and structures that we're validating. And also understand how the gas containment membrane behaves during cycling. So if we have a small-scale project We don't need a large storage volume, or we don't need a large pumping volume, so we can run many, many cycles a lot quicker to have a look at fatigue behaviour, etc. Quickly, rather than blowing up large pilot plants. And we can test many different alternatives, you know. So what we're not sure of is what's the best material. People talked about steel. People talked about polymers. People talked about unlined caverns. Again, I'm definitely not brave enough, but I'm willing to give it a go if you'll have me on your team to try unlined caverns. But there's infinite possibility of what can be tested. So it just provides an avenue for testing various permutations in a real-world environment. And that's one of the reasons that Fortescue and ourselves approached Hagerbach. One thing I will say, it doesn't actually show it on this slide, but the cover here, we get further into the mountain as we go north, and the cover is about 100 metres at this site, ranging to about 160 metres up here at this sort of contour level here. So there's plenty of cover in that respect, and the rock mass is possibly able to support the pressures that we're looking at energising to. And this is a bit of a wacky scheme, an out there scheme. So I did a bit of a calculation on what would it take to power Sargans with hydrogen. So as good as I am with a calculator in an airplane, we estimated about 70 metres of tunnel would be required at Hagerbach. The energy here is relatively green, I understand. So we could take it off the grid and demonstrate this model, you know, of intermittent supply, electrolyzers, storage, and fuel cells, and exporting out to a local city. One thing is generating hydrogen and storing it, but then there's a whole infrastructure that goes with actually taking that out to a grid and actually bringing that electricity in. And I guess this facility provides a basis close to a city with the infrastructure available to test not just hydrogen generation and hydrogen storage, but hydrogen distribution in Sargans. So 70 metres would give Sargans 12 hours of electricity. 140 metres of tunnel would give us a bit more. And obviously, if we can open up larger caverns, etc., depending on the size and scale of things that we can do, the geometry's endless. So I thought I'd just leave it at that, with a couple of thought-provoking ideas of what could or can't be done, and I guess someone's got to take the first step.
Perfect. You need to repeat.
Okay, I just wanted to understand a little bit better. What exactly means 70 meters of tunnel supplies Sargans for 12 hours or something?
So it took the largest tunnel, largest sort of cabin size that you have at the end of these. If you go back a little.
No, this one. 72 meters of tunnel could supply Sargans with green energy over 12 hours.
So we need to store about 2 tons.
Okay.
So we took sort of this size cabin, or what we think is reasonable to be made outside from the 3 sites that you identified, where we could extend the gallery. But we need to store between 2 and 5 tons of hydrogen, roughly, to power Sargans. And I've kind of just made that up based on the size of Sargans and the sort of electricity demand we need, give or take a little bit. If we make a bigger cavern, it doesn't need to be so big. But we need between 2 and 5 tons, say, to run Sargans as a pilot.
Thank you, Anmol. And by the way, as we heard Saurabh also, we can also make the green hydrogen, not just of the grid, where we have a lot of water, that's right, but maybe it's not 100% all green energy that we have supplied from outside. We can produce this directly in here as part of the subspace Energy Hub solutions. So I'm also happy to have from the Federal Office of Energy, Stefan here, because I think that is one of the targets here in Hagerbach. We have an advantage. You saw this picture, and as Anmol said, here it's about 150 meters of overburden, but we still have a freedom to operate which is much larger. We can expand our underground facility within the perimeter of permit that we have, we can triple and more what we already have. And the deeper we go in, there are different layers of geology, and of course also more overburden. So dedicated research definitely can be done in the research infrastructure, and we can start tomorrow. That was one of the reasons why we discussed this also with clients like Fortescue, because we don't need to get outside dedicated permits. Of course, we always talk with the authorities, but basically the research infrastructure is built and made and is here to do exactly this research, together with partners like you. And this is the aim also of this panel. And so I think it's good that you know these things, that you saw this, what we already thought, and what the power already on a small demonstrator scale can be to showcase what we have. And we want to talk about these opportunities. So Pascal, I would like to give the word to you, because you have a lot of experience, saw different things. You are the first time here. We made yesterday a tour. The rest of you will do the tour right afterwards through the gallery. But what are the first thoughts that come to you when you hear this? We have a lot of challenges, but we have a great opportunity also to study very detailed questions.
The first thing that I have heard since this morning is that we are all working on the different things. Sometimes the concepts are nearly or strictly the same. And I have heard that it's difficult to get information from what has been done already in the past, what has been working in Scalene, for example, for natural gas. And the second thing that I have heard, it's also different things, not only hydrogen, but also compressed air, also ammonia, also different products. And I think the problem, and everybody, it's difficult to communicate and it's difficult to get information. Why? I guess because there are some financial impacts. Okay, if there is some financial impact, it means that there is a future for this. So it means that there are opportunities for everybody. So maybe not for tomorrow, but in several years, there will be opportunities. So if we want to make the things moving faster, maybe we have to find a way also to share some information. And sharing some information on the different things, on compressed air, because we have to learn from each other on different things, because the liner for the ammonia can be something which can be used also for or similar issues as for the H2, or similar issues as for the compressed air. And one way maybe to try to find some collaboration and easier way to share the information might be also some testing facilities, for sure. So, because we feel that we have to test nearly the same things. We have to test the material, and then we have to test something which is proof of concept. So the size might be different. Here, the size of 70 meters of tunnels is something already quite big. It will be challenging for the plugging, for the pressure, for different things. The cost will be higher. I am great also to hear that if this one is operated, it can be operated and then shared with Sargans or whatever. So it means that there will be a need of an operator also, and Geostock, we are also operating the facilities, so it can be also an opportunity. So what I have seen, because it's the first time for me here in Gerba, and I have seen that you have, I was not expecting so wide range of different possibilities of testing here. So you have a lab, a quite comprehensive lab with plenty of things that can be done. You have opportunities also to expand. As you were saying, one of the issues is the fast way to start, and here you are ready to start nearly tomorrow, I can say. So this is a great opportunity also. But okay, so it means that we have to find a way not to test everybody on each side, because it will take too long and it will be too complicated maybe. So maybe it's just a wish, a great wish, but it might be very difficult because of the financial impact issues of this. But this, for me, is the only way to move faster, is to try to share some information and then to do some testing all together, at least on some concept. Then everybody can have his own concept, can develop his own technology, and can try to find his own market. But I think the market for H2 storage would be huge in 10 years' time. For me, as I was saying since this morning, it's not for tomorrow. It's not for the, maybe I'm wrong, maybe it's for 2-3 years' time, but for me it's more in 10 years' time. For the big capacity, I'm not talking once again, not for the mobility which requires smaller storage, it can be faster, but for huge capacity it will be maybe in the coming. But this one, we need time to develop all this technology and to pass all the steps, because there will be, for me, this one I still keep in mind, authorities' requirement might be a final step which will be difficult for them to be convinced and then to allow this technology to be developed, because hydrogen can be scary for plenty of people. When you refer to projects, for any kind of project anywhere, there is always a lot of people protesting and saying no, it would be too dangerous for the environment, for the safety, for whatever. So it's very difficult to convince authorities also. So this one will be a final step for everybody, because this one, it will be a common regulations, at least country by country. But I guess that some countries will copy from one to the other one. It's nearly, when one starts, the other one will copy. So
still a lot of different places, and I think, yeah, well, if you really want to go for a proof of concept, you mentioned 1 to 3, 1 to 2, real scale, 1 to 1 scale, but even there, we can start 1 to 1 scale. Maybe it doesn't need to be then 100 meter broadness or size. We can already do real scale in a 50 meter and 5 meter diameter. You mentioned that you do 10 meter times 3 meter in a steel vessel, but to go to a next step and to really see at the hard rock potential that we have here, we don't need to expand to such a huge dimension.
But even for this size of scale, there will be also financial aspects, so it will be costly. So if everybody goes for his own, it will be much more difficult than if we try to find some way to share some testing, some tests to be done, and then to share some technology and to share the results of what we get. But this is maybe just a wish, which will be difficult. But
I mean, from your experience also.
Yeah. I've had a great pleasure to be here in Hagerbach a couple of times. The last time was back in December 2022. And one of the things that came to my mind at that time, and which I promoted when I came back home to Trondheim, was that if we would like to be a part of something larger, a community, a technological community, than we have back home in Trondheim, we should join this Subspace Energy Hub, because the possibility here in Hagerbach is so fantastic. We have the possibility, if you go back to that slide with the locations, yes, we have so many opportunities to do testings. And that is absolutely something that is lacking worldwide. I know maybe a couple of places where they do have some real underground testing facilities, but not very many. We do not have it in Norway, and I wish that we could have had, but I understand that it is also becoming a huge investment to start to make something like this. So if we go back to 1969, when Neil Armstrong landed on the surface of the moon, and he said something like, a small step for a man, a giant leap for mankind, or something like that. And if we would like to move along this ladder of complexity, which I showed you this morning, we have to make scale tests to be able to take that giant leap at the end of the day. He talked about 8 to 9 years or something. Wasn't that in your presentation? It will take quite a bit of time to get there, and we need something like this to be able to take this step by step to actually reach that level where storage of hydrogen, being lined or unlined or with polymer or steel or whatever, is actually going to be a reality.
Maybe I open the discussion also to the audience, because I think then we can make a final round, if we may wish, what we can do here, because I think we have all a common interest. So the subspace brings partners of various expertise together, and we have the opportunity to realize something here, but we should find an agreement also with what type of proof of concept we want to start with. Of course, there will be a financing issue, but we know that there are also instruments available, not maybe not all in one, but we have possibilities, and there is a societal interest back to this also, and not just from Switzerland, but also from Switzerland there are clear interests behind. So I think, yes, we can shape something. And maybe I ask first to the audience if there are special questions also to you as experts, that we then can come to this final closing round about this question.
Were you mentioned, or?
Anywhere up to about 200 but the good thing is that the cover is here. So, you know, the size of the tunnel and the amount of storage we need and pressure, you know, it's just that everything is available here. And we don't, if we want to use Sargans as a smart city, it's only 5 tons of storage, so you can make that in pressure or temperature size however you want. But it's not a big number, is what I'm trying to get at.
I see, yeah. From the perspective of the use of the hydrogen, I mean, powering the city may be slightly complicated, but the approach of providing the hydrogen probably for mobility application may be a more viable solution. So that's one comment I wanted to just make.
But definitely making use of proof of concept is definitely the best solution. Because if you spend the money only to test without making use of what you have built, it will be a waste.
Well, and it's easily accessible and can be showcased really to touch and to do these learning steps. Lessons learned, Maurizio, you mentioned this. With each installation, with each doing, you come up with additional new questions and can further develop the prototypes and further improve and do the optimization path that is anyway needed.
Yeah, because even during the operation of this proof of concept or small scale or whatever you call it, there will be a need also of all these cycles, all these different various steps of operating, because this one will also be required for future large scale operation. So it will have to be operated with different cycles, different pressure, different time.
I think that this is one of the major problems, cycling.
Yeah.
Because it's, when you design a power plant or you design a storage system, you plan, okay, 25 years, 30 years, 40 years. And this means, in this case, cycling daily probably, or I don't know, depending on the application you do, on a very large environment. And it's not just aligning, but all the rest, and how all the rest behaves. I think it's a very complex point, yes, that should be explored with pilot.
With accurate monitoring around, and then.
Yes, what would be the cost estimation for the 5-ton system to implement this here in Hagerbach as a pilot? Was there a cost estimation made?
I don't deal with money. Just a designer. So I have no idea.
We were not yet there, because to do this you need to have some preliminary additional information, also pre-investigation on the progressive things. We don't have yet all the knowledge. So we were in a stage to do very, very rough first estimates, and then to say, okay, if we had this, then we can also see how the constructability of this will be, and this has a huge impact. So I cannot say anything, but
beside technical aspects, it became apparent through all these presentations that funding is a key element for sample testing, prototyping, small pilot plants, whatever. And the question, in my perception, Fortescue was, let's say, a private initiative by a company. Well, on the other side, when we were at Bolleccio for this KS study, it was partly funded by the Ministry of Energy of Mr. Oberholzer, Stefan Oberholzer. So the question is, first, why was Fortescue, because obviously Fortescue stopped, put it on hold, never went for a public funding because it seems to be expensive to go into real. We saw from Mr. Brown, we saw some figures, so it is costly. So why didn't go Fortescue into searching for funds from Australia, or if they are global active in other countries, why they were so let's say privately restricted, if I may call it like that? And on the other side, the question goes maybe to you: how much is the public authority? How much would the public authority be ready to fund, and under what condition? What commitment would the private sector need to provide that a public authority says we add up to, let's say, 10% or whatever? So these are the two questions, first to Betty and then maybe to Mr. Oberholzer.
Yeah, I think Fortescue being a private company, obviously for them there's a vested commercial interest later and intellectual property vested in their investment, which no one probably wants to give away, you know, if they're investing this much money and then someone else is making use of that knowledge, which is a little bit unfortunate. And so I think maybe there's a marriage needed between private companies and public realms to actually get together at the table and say, look, what can we do together and what can we share, and what can companies like Fortescue retain that keeps them competitive as an edge, but also, you know, that there is a collaboration, and that really needs to happen, I think, is that collaboration of senior management from private and public sectors.
That's what I understand. These caverns you built in Norway, of course, there were private companies involved, but it was funded to a large extent, if not 100%, by governmental investments, right? So the knowledge as such was created within the industry and was with the industry, while the money came from the state, or was that not the case?
A lot of the knowledge was created within the industry and was kind of distributed among the partners or the participants of the industry, yes. But what came to my mind is that we may not necessarily only address private money. There is also something called EU, which is funding research projects, and utilizing Hagerbach as a hub in that particular sense means that we all gather around Hagerbach and use that as our prime instrument towards EU to catch money from that organization. And then develop this thing around Hagerbach, which means that testing and things like that will be done here, and Hagerbach is the hub in this collaboration, so to say, European, taking with us Norway, Sweden, Denmark, and Central Europe, and maybe even Australia could do or could participate in EU applications. I'm not sure, but I do believe so.
It's certainly a good point, but you know, in Switzerland have like the Norwegian very special relation with the EU, and if we talk about Australia, bilateral cooperations topics are always a big. We are very open to do this, absolutely, but maybe Stefan, you can say more about these cooperation possibilities, I don't know, or financing possibilities.
Yeah, first I would like to say, as I learned a lot here today, and I have the feeling that it's really a very international topic, and with a lot of input from many countries, and a lot has already been done. So I would also think this would be, if one should do something here, for example, then this should be definitely done in an international context. In the IEA, in the International Energy Agency, there is a task ongoing on underground hydrogen storage. I mean, this could be one path to We are currently not active in this task. It's, I don't remember the number, but this could be one instrument to use to collaborate. I mean, Norway is very active in this program. Then there are European collaborations like CETP, Clean Energy Technology Partnerships. These are calls where we also participate, which is much more bottom-up organized, where one could, in an international context, submit something around this. I have not fully understood yet from the talks this morning where are the key R&D questions or things to address here. I mean, what are really exactly, I mean, it seems that there's such a lot of things already been tried and it's not something that is completely new. And as a non-expert, for me, this is not yet clear exactly what, if you talk now about the project, what exactly one should do. And then finally, is the question of application. I mean, we are ready to support R&D and innovation also with the sense that there is knowledge creation, clean tech and so on, which perhaps is not applied directly in Switzerland. If one wants to do something here which is of use, then or should be used in a daily manner, then I don't see it directly. For example, talking about mobility is organized like this in Switzerland, that there's no storage involved. I mean, it's produced, it's going to the refueling station, consumed there, and then delivered again. So there's not too much storage involved. So if one wants to make this a demo, then it should be much more clear what is the demo aspect here.
Mm-hmm. Christian?
Of course, some of you have already understood that I'm very interested, if not obsessed, by cryogenic storages. And my question is, if you look upon testing of various elements on a cryogenic storage, what kind of possibilities do you see you have here? Because I can see that when we are talking about mobility, of course, the cars, the things are with the distance between, or say the mass of or volume from cars and the distribution of filling station and so on and so forth, you require maybe a very much more distributed elements. But when you are talking about marine industry or say shipping, and where you are talking about green routes, you know that the Australians, the Asians, Europeans are talking about green routes from Antwerp, from Rotterdam, via Singapore, through to Australia, to Japan. All these will have central hubs where you would require quite large storages of ammonia. And all these storages is going to be cryogenic. They are going to be refrigerated or liquid CO2, liquid ammonia, meaning minus 33 centigrades. And then with various quality of rock, various opinions on safety and all these elements, what could be done here to make the proof of the pudding, so to speak? Yeah. How can you demonstrate to this environment where you may have large hubs scattered around the globe, where you may be able to attract a common interest into making large storages for this one, and for serving fueling purposes for ships, but maybe also in a larger scale for security of energy, because when you're talking about rock cavern storages, I think, Pascal, you have been working in UAE on crude oil storages. Of course, that's an energy storage. It's not just a logistic storage, it's an energy storage. And you have in Europe, you have large salt caverns and other type of storages which are energy storages. And I think the imagination is what limits here. And having the rock overburden you have on those orange colored, I'm 100% sure there is a lot of cryogenic testing which could be done there to demonstrate that this is a safe way of storing, and also maybe with different rock qualities elsewhere to demonstrate that no matter the quality, the possibilities are there. And instead of overfilling already congested harbors with surface tanks, if you can put them underground, I'm 100% sure that this would make amends into this environment.
There's certainly potential, yeah. Well, with cryogenic storage, so I personally do not really have experience here, but I think there are some possibilities, but maybe Mr. Amberg...
No, I'm not. I have something else to say.
So no. Please.
No, I mean, let's say there seems to be a quite common understanding one should go into whatever type of research development, stage-wise, huh? So, and we are more than pleased that obviously a lot of people around in this panel, they think Hagerbach could be the infrastructure or provide the infrastructure to do certain things. Provocative question: if Hagerbach reaches out to everybody sitting here with a, let's say, a kind of rough draft of what could be developed, asking you, do you contribute? Are you willing to? Based on an NDA, would you then contribute in such a research? Would that be a way forward to go from the talking to the walking, from going into action? Or do you say, well, we all know it should be done, but please let pass that cup. I do not want to, because there are other issues on my table which are more important. So just a provocative question: if Hagerbach as an infrastructure provider says, okay, I reach out to most of you because you seem to have an interest, and I put a rough proposal what could be a stage-wise development, would you join in or would you not join in? What do you think?
I'm not the only one to decide. For me, it's the best wish. Once again, there are so many different interests in this. Our other company is a construction company. If I ask them to share the knowledge with other construction companies, such as some of your partners here, whether they will be willing or not, I'm not quite sure. Personally, I will try to convince my company that without sharing the testing, without sharing, we will not move forward, because it will be too costly for us, it will be too long, it will be a waste of information already existing. So I will try to convince. Whether I will succeed, I cannot guarantee. But yes, having what I hear from you is having a leader and saying, okay, we set up this one and all these different persons are making it together and we define what we have to test.
I'm not so much talking of a leader, because it's not clear who will be the leader in the different technical tasks. So, and what is to be for just acting as a kind of catalyst, as a kind of crystallization point. That is what because Hagerbach is just an infrastructure. So ultimately Hagerbach is not doing the research. It just can act as a catalyst to enable, and the Subspace Energy Hub in this sense is the platform for this catalyst function. And then reach out to those who have declared an interest and to say, look, this is a proposal, would you join in based on an NDA, just to make sure that it's clear who, et cetera, et cetera. The question is just, if Hagerbach or Subspace Energy Hub acts as such a catalyst, would that find interest? That is my simple question. It's not that you can't give any commitment, yes, I will invest, that's reasonable. But the thing is, does it make sense from the subspace to say we work on that, we spread that, and ultimately we can put together a team with a certain perspective? Would that catalyst function, would that find a proactive, supportive feedback from your side? That's the question, please.
Oh, sorry. To answer your question directly, would I personally contribute? The only thing I have to contribute is knowledge, and I would definitely contribute because, we have to do it by 2030 or 2050. We have to do it. But I think from what you're saying, the catalyst is important because at the moment, as much as me and Pascal might like to go and talk about lined rock caverns and bars and whatever, we're limited because we don't have, our parent companies do drive what we're allowed to share and whatever. So I think the catalyst would be Hagerbach providing a place to collaborate, but also bringing the parties to the table and saying, look, what are you willing to share? What are you willing to do together? And if we do this, what will you take away and still have commercial advantage? Because we can do it separately and we can all spend 100 million each, or we can do it together and spend 50 million each and still take away. The geology and the problems of Australia are different from the geology and the problems of France. We'll never have one solution fits everything and all, but the catalyst would be bringing these people to the table. And if you want me to tell you about equations and stuff, I'm in. So from a knowledge perspective, yes, but I think you have to bring our commercial parents to the table to see what they want to share.
From knowledge perspective and from technical point of view, since this morning it seems that we all have the same things and we need the same things to move forward. Maybe in different ways here and there, but we are on the same line of moving forward. There is a need for this. There will be a need of large capacity storage in the coming years, maybe 5 years, maybe 10 years, whatever. Maybe it will be with a steel liner, maybe it will be with a polymer liner. This one has still to be defined, but there is a consensus on yes, we need to move forward and we need to test different things. We need to test the materials and then we need to test a small facility, whether it will be on a 10-meter long tunnel or 70-meter long, whether it will be, yes, we are coming to the same. What is stopping us to move forward right now? It's this intellectual property and these financial issues and this. But there is a need. Also, if there is a need, there is also a commercial opportunity in 10 years. So I don't want to give up on these commercial opportunities. I don't want to share. This is all these issues that has to be discussed. Yeah.
If I may add something, please. Okay.
Pardon? Yeah, just directly to your answer, not to your question, Felix. Yes, that's why we are here. SINTEF is very much familiar with working in the landscape where there is a lot of IP things floating around. So, and we have been doing that for 50 years, 60 years. So there are routines that can be used to actually be able to work together and still maintain what is the commercial, high points that are needed. So, it's possible to do it.
So I would suggest that we pick this up from the subspace also, that we really try to formulate something together. What type of project, stepwise project for the hydrogen storage topics we can do. We anyway need to follow up after this meeting. I just give you the word soon, and there was Matthias also, but watching at the clock and knowing that some of you have restraints and need to leave shortly, we need to come to an end. There is also a tour scheduled for those that have an interest afterwards. So yes, please take this short, you, Matthias, and then we
I just wanted to make a short comment because I, with the team, worked hard to bring all you people here and discuss about this, so we better have some clarity and shed some light on the challenges and the opportunities. And for example, as Mr. Oberheiser mentioned, we hear you about the complaints related to cost and the funding opportunities, but on the other side, we also see the funding institutions that they lack some clarity on the challenges that you're facing, or what are exactly you looking for to go for in the testing, and there seems to be some issue with the communication here, and this is something that we really wanted to help with by filling in this gap, and hopefully we can make use of your technical knowledge and experience, and also make use of our connections and institutions that are related to our network of partners, with coming with some funding opportunities and taking some small step forward, and then bigger and bigger until after 10 years. So, yeah, Matthias?
Yeah, sorry, I don't think the discussion I want to have is a short one, but it's very practical. I mean, I'm not sure what the Swiss authorities, how much hydrogen they would be happy for you to pump into the mountain here. I think that would be a lot of convincing work actually to do. So maybe we should start a bit differently and for example, with this compressed air approach. I mean, with compressed air motors, you can take, you know, peaks of your grid, and that could be very useful. And I don't know whether I presented that very well, but one of my main concerns are actually fatigue issues over time. You know, the daily pressurizing and depressurizing, and this, at least part of that, we could actually test with compressed air very well. We don't have the long-term effect of hydrogen in that case, but at least we have some thing, and that could also be a part in the puzzle to convince authorities to do the next step with hydrogen, probably with the majority of the same infrastructure.
Thank you very much. I fully agree, because as mentioned also, Anmol, you also said it, it's about different types of materials, different pressures, lining, tightness, different circumstances, and we can really take them step by step, and there we have common interest, be it in compressed air, be it in hydrogen, be it in ammonia, cryogenic you mentioned, maybe also this can stepwise be included, but it's a common topic. It's the storage gas liquefied in small, medium size, large scale, and we have the opportunity to implement this here, and based on this I think in the subspace we will continue to work. This was the first roundtable in these circumstances here, and I think we will repeat one. I learned that we should have next time hybrid here. Maybe we get them. But we will continue, and we will keep you involved, and of course we are happy also that the partnership within the subspace is growing, because more expertise and competences we bring to the table, the faster and better hopefully we can go this way together. With this I close. I don't give the last round because we are really running out of time. I thank you very much for all the contributions, all here on the panel, all panelists that have been up here and contributed, all the audience for your patience also. We are a bit over time, but for your interest, thank you for coming here, and we will take the recordings also, we will cut them, we will also spread them among our channels within the Subspace Energy Hub. With this, I also thank to you, Aurora, for coordinating, for organizing this panel, and maybe our president wants to have the last word. Not necessary. No, but maybe Aurora, you organized it. The last word is yours, please.
The last word is thank you very much, and we should take a group picture now. So I appreciate it.
Good.